Hello, good morning, good afternoon, good evening, wherever you are. Welcome to today's webinar. We are going to start in a minute. Just want to do a quick sound check. If you can tell me if you can hear me well and if you can see my screen, just to make sure that everything is working.
I hear you.
Okay, perfect. Thank you so much. Thank you, Victor. So we're going to get started right away. I will adjust the sound and get started here.
Hello, welcome everybody to today's webinar. It's about the recent dam breach modeling advances in RiverFlow2D for water and tailings dams. My name is Reynaldo Garcia. I'm Director of Development and Applications at Hydronia and Hydronia Europe. And I will be joined also by Nick Calero, who will be helping with the tutorial that we are going to present today. So the overview of the webinar, we're going to talk about the RiverFlow2D model, the updated dam breach component, and the dam breach tutorial will close today's webinar. That also will be followed by a question and answer period. I want to start by acknowledging the many people that have contributed to all the things that we do in Hydronia. First, the people at University of Zaragoza, led by Pilar Garcia Navarro. Also to Brazil Hydro, who is our representative in Brazil, and it's led by Adolfo Correa. And of course, to the many people that help us here in Hydronia that are contributing quite a lot to the development that we do. Of course, I need to always recognize the many clients that we have, that the users that help us all the time in improving the system, and many of the things that we develop are based on the needs that we get from the users that request new features and things like that, and we really appreciate that support from all of you. I want to start by giving a very brief introduction to the dam failure modes, and this is just a very short description of the things that motivate this development. So it's in a way a comprehensive review of this type of phenomena that occur in many countries. But I want to mention that some statistics about the dam failure. And according to the American Society of Dam Safety Official, ASDSO, 34% of the failures that occur in dams are due to overtopping, and 28% by piping, and most of the rest is due to foundation failure. So if you look at this, you can think in, in general terms, 1/3 of the cases are overtopping and 1/3 is piping. So 66% are responsible. The overtopping and piping are responsible for 66% of the cases for dam failure. So it's very, very important to understand that these are the main failure modes that occur, that has been observed in the many failure of dams that have occurred. Now, in terms of the primary mechanism that include, of course, overtopping and piping, but other modes as well, you can see in this graph that is from the damsafety.org site that by far the overtopping and piping are the main responsibles of the most of the failure modes. You have others, minor cases that includes spillways problems, structural problems, the capacity of the spillway, foundation, some erosion in lateral structures, and some other minor things. But for the most part, the overtopping and piping are the main causes. In terms of the cause, what they call the incident drivers, or the main causes of the dam failure that in the first place will lead to overtopping and piping, we can include the hydrologic flooding, that is also by far the main responsible for this type of failure, but also seepage and internal erosion, that is the main driver for the piping failure. Then there are others that are also included in this chart here, but they are not so important as the hydrologic flooding. So what happens typically is that you have a really extreme event. That extreme event overwhelms the capacity of the dam, and then you get the overtopping. And that's that extreme events is the one that will lead to the overtopping failure. The case of the piping is more the seepage, and is a much slower developing failure mode than in the case of the overtopping. Now, the overtopping failure mechanism can be described by an erosion that occurs initially in a gradual way by the overwhelming capacity of the reservoir. So the water comes over the dams that can contain some deposit initially, and that water that comes over the spillway or the dam itself starts eroding the dam body and eventually leads to its total collapse. And once the breach forms and communicates the reservoir with the downstream area, then it's a matter of time that the collapse, total collapse occurred. What I'm showing here on this graph is actually a tailings dam. Yeah, and this is a typical upstream built dam that is it's not used that much anymore, but there are many dams that have been built in this way. So what happens in this type of construction, you have you have the need to create a deposit for the leftover of a mining operation. So you first build a dam like this, and then you fill this deposit. But you need more capacity, and it's filled already, so you build another dam a little upstream from the first one. then you have a second deposit, and you fill it out, then you build a third dam, fourth dam, and so forth. So the problem with this is that even though maybe the first dam foundation was well conceived, the others are founded on previous deposit of the tailings. And that creates sometimes instability on the structural conditions of these dams. And also, they tend to be very susceptible to the overtopping failure due to the overwhelming capacity of the upstream dam itself. So you get overtopping not only on water dams, but also on dams that have been built for containing tailings from mine operations. In the case of the piping failure mechanism, this is a completely different failure process by which you have initially seepage that occurs from the deposit that you have upstream into the deposit itself and through the dam body. So what happens is that initially the seepage is very small, but as time progresses, what happens is that the seepage through the soil and the material that forms the dam and the deposit starts to increase in velocity. And that increase in the internal velocity through the pores of the material has an erosion capacity that increases with the velocity of the water. So as the water velocity increases, you get more erosion, and the erosion increases the porosity of the material, and as time passes, this porosity is so high that then you get pipes, what they call pipe, and that's why they call it piping. So you have these large conduits that communicate the water to the downstream area. And at some point, if this is left uncontrolled, you will get a total failure of the dam itself. So that's a very dangerous, even though it's slower in development with respect to the overtopping failure mode, it's a very dangerous failure mode. And it should be at least analyzed in many dam failure risk assessments. Now, the model that we developed is the RiverFlow2D. And this is a two-dimensional hydrologic flexible mesh model that deals with water and non-Newtonian fluids. So we can have the standard two-dimensional shallow water model for water, but also can take into account the characteristics of the non-Newtonian fluids, which are the tailings or debris flow type of fluids. It uses a state-of-the-art finite volume numerical engine. And this is important because the finite volume method that we employ in the model, it resolves many of the failures of the older numerical models that used to be used in older models, like, for instance, finite differences or even finite elements. The finite volume has the intrinsic characteristics that it can conserve in a very exact way not only the volume at the cell level, but also the momentum, while the numerical characteristics of the finite difference methods couldn't ensure that you have the full numerical conservation properties of the finite volume. And that's one of the reasons that this method is being used more and more in modern models like the RiverFlow2D. The model can deal with supercritical and subcritical regimes, which is important for the type of rapid events that occur in dam failures. It can have, it can consider hydraulic structures such as culverts, weirs, bridges, gates. It can do bridge scour and dam bridges, as we will see. It works in English or metric units, so it can adapt to different countries' standards. It has a graphical user interface that is based on the QGIS software, which is an open source free software. And it can do a number of mapping tools that can create maps for all of the hydraulic results of the model, like velocities, depth, water surface elevations, but many other plots as well, like hazard mapping and also animations. The model runs not only in CPU, which is the main processor that most of the computers have, but also runs in GPU with cards, in NVIDIA GPU cards. And the advantage of the GPU cards is that if you have a model that is able to take advantage of the parallelization power of the GPU cards, the model can run significantly faster than if it was to be run in a single processor computer or in a model that is not parallelized to this type of hardware. So the speed ups that we have demonstrated, and we have many cases where we have tested this, we have reached speed ups of 1,000 times, which means that runs that would take sometimes weeks or days to run in older models can run in RiverFlow2D in a matter of minutes. It's such speed up that you could expect with this type of model. The model has the main hydrodynamic component where it solves the shallow water equations for velocity and depth, but also has modules that adapt it to different applications, like for instance, the MT, which is a quite used module for mud and debris flow and tailings dams. So if you have a case of a dam failure from a mining operation where you have a tailings deposit, then you can use the MT module to deal with that type of fluids, which behaves very different from a water flow. And we have other modules for sediment transport, urban drainage, pollutant transport, and water quality, that they can all be used in conjunction with the main hydrodynamic model. Now, the main characteristics of the numerical method and the model that as we have developed it is that it works on a flexible mesh. Now, the flexible mesh is nothing else than a triangular regular network of triangles that can have different size. So you can adapt the mesh to represent the geometry that you have, your obstacles, or even your bathymetry or your topography. And it has the power to be refined in those areas where you need more detail and be larger in areas where you don't need so much detail. As you can see here, it can even resolve the flow between buildings that have a very narrow gap in between. So that's one of the advantages. The other advantage is that if you have structures like levees or even dams that do not have a rectilinear alignment, you can create and adapt those alignments in the best way that we represent the real situation, and generate your mesh so that it will capture in the most realistic way the geometry that you have. And that is the main advantages of flexible mesh with respect to other models that use square cells that are not impossible to adapt to a real geometry as you would have in an urban area or in a natural environment. Now, the other advantage of the triangular mesh and the full solution of the shallow water equations is that the model can resolve the two-dimensional equations that do not have any limitation in the direction that it can have. So there are no limitations on the velocity direction that you get in a given cell. So they are not predetermined directions that may affect how the flow occur, depending on how you make the orientation of the mesh or things like that. So the main computational unit of this model is the triangle, and that's why the mesh can be adapted in such a flexible way to different geometries. So the main capabilities of the RiverFlow2D MT module that is used very often to solve dam breaches and dam break flooding includes the two-phase model, which is the real two-phase model where we can solve the equations that corresponds to the solid phase and the liquid phase, and generate the solutions that represents the concentrations of each phase that you have in real life. Then the model can also consider the spatial and temporal variability of density, viscosity, and yield stress. So every time step, the model computes not only the velocity and the depth of flow, but the properties of the material as it moves through the soil. So if you have entrainment of the material that will erode the soil, that material will get into the flow and vary its properties. So all of these conditions are considered in the model. To represent the non-Newtonian fluids, we offer 9 different friction formulations that cover a wide variety of possible fluids that can occur in reality. I think also that RiverFlow2D is the only model that is available nowadays that does not consider a quasi-horizontal flow for the gravity term. This means that the model actually computes the gravity terms considering the real slopes that you have in the topography, and it will not assume that you have a horizontal or quasi-horizontal situation as you do in most of the shallow water models available nowadays. This is important because the gravity terms is the one that drives most of the flow in this in these dam break situations. Also, the model can consider the initial tailings properties that can vary in space. That means that you can have different deposits with different properties, and those deposits can flow and mix with different water bodies that you may have. So you can model the mixing of tributaries that can come into contact with the tailings, or you can model, for instance, the flow coming out of the dam break of a tailings into a water body, like a reservoir or a lake. And then the model will determine how the concentrations of these tailings change. So you can see here, this is from Brumadinho simulation. So you have the tailings coming from this dark, is represented at this dark concentration tailings, and then you have a river downstream, and you can see how the mixing occurs and how the model computes the mixing of different concentration tributaries. Now, the bed soil characteristics can be also different from the flowing material. So you can have entrainment of material from the riverbed that can be different from the tailings, which is normally the case. Of course, to do this, you need to have multiple sediment classes. That means sediments of different properties and different sizes. And all of this is done in an environment that can compute the erosion and sedimentation with full flow bed interaction. Now, the other characteristics of the MT includes the hydraulic components, weirs, dam breach, as we will see, includes the prescribed overtopping and piping, internal rating tables and sources. And we have included recently a new basal resistant formula for frictional shear thinning and shear thickening materials. It's called the Herschel-Buckley fluid. And we also have included settling velocity factor that is specific for sediment classes. So the settling velocity can be calibrated in a very fine way, depending on how many classes you have. And we have also recently included a way to represent the variation of yield stress and viscosity with the volume concentration, not in prescribed formulas, but given a table. So if you have an experimental table where you have determining how the viscosity and yield stress vary with the volume concentration, then you can use that table directly in the model and ignore the other formulas that are available as well. Now, the dam breach component that we have in the model includes 3 failure modes: the prescribed, the overtopping failure, and the piping. We had in the past only the prescribed method. It's the simplest one, and if you don't have anything else that works, but in all of the cases, the dam is defined by a polyline, and the polyline allows you to adapt to different dam geometries because the mesh snaps to that polyline. So the dam doesn't need to be a straight line, it can be a curve or any form it has. Now, this prescribed dam breach method is very simple. It assumes that you have a trapezoidal or triangular or rectangular breach in the dam, shown here in this figure. And it's you need to prescribe the velocity at which the breach will form and evolve in time. So this breach that initially may be small will grow, will deepen here and will grow to the sides at a rate that you will need to determine and provide as a table. So one of the data that you require here is a time evolution table where you need to provide for each time the width of this breach and the height. So if you can estimate that in some way, then you can enter that table, and in addition, provide some other characteristics of this geometry here, And the model will determine the discharge through the breach at every time interval using the formulation that you can see here. I will not get into the nitty-gritty of these formulas, but they're very simple ways to determine the discharge based on the hydraulic characteristics on the upstream reservoir, downstream conditions, and the geometry of the breach as it evolves in time. So it is very simple, but the main drawback of this is that you need to know how fast the breach will form. So it's not totally physically based method to calculate the breach formation, because you essentially you need to prescribe or predetermine how the breach will evolve in time. Okay, but that's a way it was, and it still is a method that it may have some use if you don't know anything else from the dam itself. Now, we have developed two new methods that are more physically based. One is the piping dam breach, and the other one is the overtopping. First, the piping dam breach is a way to compute how the breach forms when you have this process that I briefly explained before, where you have an initial seepage, and eventually that seepage leads to a piping, an internal pipe that occurs within the soil or the material of the dam, and starts to grow in time due to the erosion. So it is actually erosional piping dam breach. It will be a more specific name to this method. So the assumptions that we make to implement this in the RiverFlow2D model includes the following. First, the cross-section of the initial pipe channel, it assumes to be an arc, like you see here, with a rectangular bottom. So initially, it can be small as you want, but initially it is of this form. And as time progresses, it expands in all directions. So it goes deeper and to the sides as the erosion process occurs. So at some point, depending on the crest elevation and the location on the size of this pipe, at some point this area becomes unstable because the characteristics of the material that is on top of this hole will not be enough to sustain the stability of all this area, and then the pipe collapses. Essentially, all this material here collapses, and then when that happens, then this material is transported downstream, and the assumption that we make here is that it's instantaneous transport of the material downstream, and then it's from that time on the failure mode becomes similar to the overtopping as shown here. So you pass from a piping to an overtopping with free surface here as time progresses, and you get the time after the collapse. So other assumptions include that the failure planes are assumed to be vertical initially in the pipe, that the collapse occurs instantaneously, and the material is also instantaneously washed away. After the collapse, then the breach continues with trapezoidal cross-section, as you see here in this figure. So in terms a little more details on the formulations that we follow here, we initially assume that the pipe is fully filled with water, and we use this formula to determine the flow discharge within the pipe. Then as time passes, the pipe becomes so big that you don't have enough water to fill it out completely, and you have a partially filled water a pipe. So we use this other formula for that purpose. And these conditions, depending on the relative conditions that occur during the formation of the piping process, we can compute the vertical erosion rate that determines how this bottom is eroded in time, and also the horizontal erosion rates. And these vertical and horizontal erosion rates are a function of the critical stress that is a property of the material that you have. So this is the critical stress required to start the motion of the material of the sediment, and also of the bed shear stress that is exerted by the flow. So of course, the bed shear stress is a function of the hydraulics of the pipe itself. So you see here that this shear stress is a function of the discharge, the Manning-Sen of the area and the hydraulic radius, and the balance of the critical shear stress with respect to the bed shear stress. It participates in this horizontal and vertical erosion rates formulas that are multiplied by an erosion coefficient, that is K sub D, is an experimental coefficient that can also be approximated by some empirical formulas. Now, once the pipe collapses, then you get the trapezoidal cross-section. But how do the model determines if the pipe collapses? Now, there are two conditions that need to occur for the collapse. One is if the top of the pipe, this point here, reaches the top of the dam, then obviously there is no fluid here, no material here, and the fluid is connected to the top. So there is a collapse that occurs naturally by that growth of the pipe. But even before that, you can have a second option where the failure can occur when this material here weighs much more or more than the resistance that occurs in the failure planes that are at either side of this cylinder, if you want to see it in that way. So if the weight of this material is higher than the resistance that you get in the soil, then you have a collapse. And when that happens, then all of this material is removed, and then you have a trapezoidal cross-section that continues to erode in time. Now, incidentally, this trapezoidal cross-section is the one that we use also for the overtopping erosion. So this, after the pipe roof collapse, the cross-section of the breach turns to the trapezoidal form, and the discharge is computed with the same formula that you see here that we showed before. Then we have also the rates of erosion that we obtain to determine how this overtopping occurs in time. So this means that the overtopping erosion, the way to compute the overtopping erosion that we use in the model is the same that we use to calculate the discharge and horizontal and vertical rates of erosion that we use after the pipe roof collapse. It's exactly the same. So that's the assumption that we make to compute the dam. This table summarizes the data required by each of the failure modes. So we have gathered here all the parameters that you will need to provide for the prescribed overtopping and piping failure modes. For instance, for the prescribed option, you need to give the crest elevation, the side angle of the breach, the discharge coefficient, and the temporal evolution file. This is the file that we discussed before that has the width and height of the breach for every time. So, and you can see here for overtopping and piping that you will not need that temporal evolution file, but you need other, in addition to the crest elevation, side angle, and coefficient, discharge coefficient, you need some other data for the overtopping. That includes the type of material, the size of the material, the critical shear stress, erosion coefficient, and also for the piping, you need also to give information about the specific gravity of the material, the porosity and cohesion, and plus additional parameters for the geometry of the dam, the crest width, and the upstream and downstream slopes that are required to compute the weight of the material that is over the pipe, and in that way determine the collapse time. So in addition, we have dialogues in the model that we have created so that you can enter that data from the QGIS plugin. So you will see in the tutorial that when you create the polyline that defines the dam, then you can enter that data. And one of the things you need to do first is to enter the failure type. So here you will have the prescribed, the overtopping, and the piping. And each one requires different data, as we saw before. So this is for the prescribed dam breach. That is the only one that requires the temporal evolution of how the width and height of the breach vary in time. Then we have the dam breach by overtopping erosion, where we have all of this other data that is summarized here. Then we have the dam breach by piping, where we have all of them. You see that they are organized in these frames here. So we have this data is for the prescribed, this and this for the overtopping, and all of them for the piping, except, of course, the temporal evolution that is only for the prescribed method. You can also modify these values once they are created in QGIS. You can use the data input program that that also provides ways to change that once without having to go back to the QGIS environment. Now to finalize, we're going to show you a brief tutorial that will be given by Nick Calero. So let's start that now.
Hello, welcome to the dam breach tutorial for RiverFlow2D. This tutorial illustrates how to incorporate a dam breach simulation into an existing RiverFlow2D project using the QGIS interface. As shown on this slide, the dam is approximately 1,575 feet long. The breach center is 550 feet from the right margin of the dam. The opening of the breach has the following final dimensions: a top width of 160 feet, a bottom width of 100 feet, and the final breach height is 30 feet. The procedure to model the dam break involves the following steps: open an existing RiverFlow2D project, create a dam breach layer and draw a line that represents the transverse axis of the dam, generate the mesh, run the model, and then check the results files. You can find the tutorial files on your computer in the directory shown. On the project menu, click Open and browse to the existing project dambreach.qgs. This project already contains the domain outline layer, the digital elevation model in raster format. Outflow conditions are set to free outflow in the lower left boundary, and an initial condition of water surface elevation is set behind the dam. Create the template for the dam breach layer. In the RiverFlow2D toolbar, click on the New Template Layer button. In the dialog, select Dam Breach and click OK. Edit the newly created Dam Breach layer by going to the Layers panel and selecting Dam Breach. In the digitalization toolbar, click on the Toggle Editing button. A pencil icon will appear in the Dam Breach layer, indicating that the layer is in edit mode. Using the Add Feature tool of the digitalization toolbar, draw the line that defines the dam axis. Keep in mind that the breach centroid is measured from the first vertex of the dam line. In this example, it occurs 550 feet away from the left margin of the dam. The dam axis is drawn from the top of the channel to the bottom, along one side of the polygon that defines the initial water surface elevation. Right-click to finish the line. Once finished with drawing the dam axis, a window to input the parameters of the dam breach appears. Input the information as seen on screen and click the Check Fields button. Click the Temporal Evolution tab and click on the Import Dam Breach File button. Select the breach1.txt file in the project folder. Click OK to close. There are two more options for failure types when setting up a dam breach. For this tutorial, we will not use them. However, we can show the differences here for future reference. The second failure type is an overtopping breach. This breach requires additional parameters for proper setup as seen on screen. Keep in mind that this failure type will not need a temporal evolution file to be specified. The third failure type is a piping breach. This requires for all parameters to be supplied by the user as seen on screen, and also does not allow for a temporal evolution file to be specified. Go to the RiverFlow2D toolbar and click on the Generate Tri-Mesh button. This will generate a mesh adapted to the domain outline cell size parameter and the dam breach line cell size parameter. As you can see, the resulting mesh shows more detail along the dam axis. Now we need to export the files to the RiverFlow2D model. In the RiverFlow2D toolbar, click on the Export to RiverFlow2D button. We make sure that the correct DEM is selected and a suitable name is given for the project. The defaults are suitable for this exercise. Click OK button and the export process will begin. Once it is finished, RiverFlow2D will be loaded with the dambreach.dat file. After exporting the files, the Hydronia data input program is loaded with the project file. Review the control data and click Run RiverFlow2D. I will not save any changes in this example. However, you may need to save changes if any parameter was adjusted. A window will appear indicating that the model has started running. The window that RiverFlow2D presents while running the model shows simulation time information, volume conservation error, the total input and output discharge, as well as other parameters as execution progresses. We will speed through this portion of the simulation. Now that the model is finished, we can click the Close button. The command line execution window should indicate that it will close in a few seconds. It is now okay to manually close the window or wait until it does so automatically. We will not save any changes. To review some of the output data, we will open a File Explorer window and look through the project folder for a file with the extension .dambreach-h. This file contains the hydrograph for the dam breach. When prompted, select Notepad or your preferred text editing tool to view the contents. Spend some time to review the output data to see the details of the simulation. Back in QGIS, we can easily create an animation of the results to view it in real time. Go to the RiverFlow2D toolbar and click the animation icon. A panel will appear under the Layers panel on the left side. In the Select Layer drop-down, select Depth and click Add Layer. Click OK to keep the default output range. Once loaded, disable any layers that we do not want to see during the animation. Click the Play button to see the animation in the map window. We can also export what we have on the map window to a movie file. Click the Export Video button. We will lower the speed so we can see each time step and select the folder and file name to save the animation. Click OK to export the video. Once the file is ready, we can open it from the File Explorer to view the results. This concludes the dam breach tutorial. Thank you for watching.
Well, thank you. Thank you very much. We actually have taken a little more time than we had expected. So I have time maybe for a couple of questions if you have. So let me see here in the. Okay. So I have a question here about the differences between the output from an internal rating table and the dam breach results. Yeah, by Camila. Camila, yes, the output from the internal rating table is in a different. It's a different file. It's a totally different file. I mean, normally you don't use the internal rating table and the dam breach at the same cross section. The output from the internal rating table is a .out file, and the output from the dam breach is in the dam breach H file that Nick
referred to. So yeah. A question is if the lateral slope of the bridge is fixed. That's a question I will need to look into. To answer, I think that when time progresses, the model calculates the width, the bottom width of the cross section, and I think it assumes that it's constant, the angle. But I will need to get back to you to give you a more definite answer about that. Sorry about that. I have a question, Ruspek. Hello, Ruspek, about the if besides the Brumadinho, if we have performed other analysis verifying the bridge module. Well, we have done a number of comparisons with USGS data for the MT module. And we have a publication that refers to that. And I'd be happy to send that and share that with you. How well can the overtopping and piping failure modes replicate actual dam breaches? Well, I think it replicates in a more realistic way since it's physically based. It's closer to reality than just using the prescribed mode. So I would suggest it's better in predicting those kind of situations than the prescribed option. Roosevelt also asked if we have an output to visualize the spatial sediment deposit pattern. Yes, of course. We can output the changes in bed elevation or the bed elevation at different times, so you can see how it varies in space and time, the bed. Yeah, that works in both in the sediment transport model and also the modern tailings model. Yeah. Danielle asks if can I use as input a volume elevation curve instead of an initial water surface elevation condition computing the DM. Volume elevation, actually you can import a raster for the initial elevation that is variable in time. We do not have the option of volume elevation curve for reservoir. But that's something that we could develop. It shouldn't be a good addition, I suggest. Yeah. Okay, I have another question here. If the tool is available already, yes, the tool is available in the latest update that we have just released, 8.04 version of the model. Unfortunately, I have several other questions. I don't have time. I ran out of time here. We ran for an hour, but we had only 45 minutes originally. And but I will I'll try to answer your questions by email after the webinar. Remember that you will get the video of this webinar. You have the option to watch it later. When it's processed, you should receive an email about it. So thank you so much for attending today's webinar. We really appreciate your support and your interest in our products. And I hope to see you in the next time. Thank you so much. Bye.